Hello everyone, welcome to this lecture. Today I'm going to talk about MIPS assembly programming, which is essentially learning how to do assembly programming on MIPS microprocessors. So you remember from lecture 3 on Python programming that programming comes at different levels. At the lowest level, we have machine languages, in which instructions are just zeros and ones and numbers and so on. But then at the next level, which is a bit high level, we have assembly programming, which we'll see how it works today. In this level, we are still very close to the architecture of the computer, to how the computer is built, how the memory is, how the processor is working, and so on. But we don't have purely numbers. There are some names that are associated to the instructions, and we have variable names that we can use. And we had seen before in Python programming that we were almost independent of the computer architecture. So in Python, when you write a program, it is going to work on any computer with any processor and any operating system. But we will see that in assembly languages, it is not like this. So today, as I said, I'm going to talk about assembly programming for MIPS processors. So every processor and every version of a processor has its own assembly language. These the assembly languages have a lot in common in how they are formed and so on, but their details vary a lot. So let's see first what a processor is. I'm going to talk about this just very briefly. And let's see what MIPS processors are. And then we continue from there to see how is the assembly language for MIPS processors structured. So a processor is often known as a central processing unit or CPU of the computer. It is a circuit much more sophisticated than the circuits that we had in our second lecture. But it is essentially a circuit that performs all the computations in the computer. I should correct myself. It doesn't do all the computations, but it does most of them. We can have other processors, for example, GPU, which is the graphical processing unit, that does other kind of processing. So today I'm going to talk about just CPUs. And so when I say a processor today, I mean mostly the CPU, not GPU or other processors that you can have. So CPUs do arithmetical and logical and even input-output instructions. For example, when you want to read or get a data from a user, or you want to pass some data to the user, or you want to store something in the memory, all these things is done by the CPU. So these instructions that the CPU wants to do are all passed to it, usually in our computers that we use, are passed to the CPU by the operating system. So the operating system is actually the subject of our next lecture. So some things I will give some rough idea of how CPU and OS work in this lecture, but we will see more in the coming lecture. So each CPU has usually 4 basic elements. One is called ALU, or arithmetic logical unit, which does, as its name suggests, the arithmetical and logical instructions and computations. And the CPU also has FPU, which does floating point unit. And the CPU has also registers, which are a kind of memory which is very fast, faster than your main memory. And it is very expensive as well. And there is also another type of memory in the CPU, which is also fast, but not as fast as registers. They are called cache. So we are not going to go to the details of how OLU and FPU work. We just get a brief idea of how they work together in a CPU. So both ALU and FPU do arithmetical and logical operations on the numbers, and they send their results to registers. And there is also something else that is stored on registers, which are the instructions that are going to be executed. Cache is another type of memory, which is a small part of the total amount of memory which is on your computer, because it is very expensive, but it is very fast and stores copies of data that is guessed that it will be used in future. So it tries to guess to bring you the data that you might use in future, so that it makes your work faster, because fetching data from the main memory of the computer is very time consuming. In terms of the speed of computers, it is time consuming. So computers prefer to use cache if there is such possibility. For example, when you visit a website, it is also common that it is stored sometimes in your cache, so that you can retrieve it faster next time instead of just download it from its server. So now let's see what is MIPS. MIPS is a type of processor, is a type of CPU. And MIPS stands for microprocessor without interlocked pipeline stages. When we say processors, we actually mean microprocessors, because you remember from the lecture about the history of computers that when the transistors were evolving during time, so then microprocessors achieved, which microprocessors appeared that have like thousands or millions of transistors on tiny spaces. But for just being brief, we sometimes say processor, but we always mean microprocessor, because nowadays just microprocessors are used everywhere. And the fact that it is pipelined means that we will see in a diagram later that it means that several stages of computation can work in parallel in MIPS, so that the execution time is reduced in total. So MIPS, because it is a processor, it has its own assembly language. And so you should know that besides MIPS, there are other types of processors, for example, Intel, ARM, Spark, etc., etc. So they differ with MIPS in terms of their execution speed and efficiency and their price and where they are used and so on. So MIPS is used for this lecture because, or it is usually taught with in computer architecture lectures because of its simplicity of assembly language. Let's see at a high level how a CPU works and what different stages its work has. Because MIPS is a CPU, and knowing how CPUs work gives us a better idea of how MIPS works and what do the instructions that we are going to use in our assembly program mean and how they are going to be executed. So the assembly instructions that are given to CPU are stored in RAM, are stored in random access memory, and that the first they have to be fetched, or they are going to be read one by one from memory. Then they are given to a decoder, because these instructions are in assembly and the computer doesn't directly understand assembly. What it understands is machine language. So these are translated to machine language and they are converted to signals that will trigger different transistors to do these computations. And The registers here show the data that will be manipulated in each instruction, and the actual computation will take place in ALU. So the ALU will take the inputs for its executions from the registers. It will read them from registers. Every data that needs to be executed needs to be either loaded in some register, or it has to be immediately given as a constant. We will see them in later slides. So then ALU gets this data and performs the operation. And from the instruction decoder, it gets what sort of instruction it has to do. For example, is it a multiplication or division or addition whatsoever? And it will do the computation and then write the results to memory or to the registers, depending on the type of instruction. So here we see the architecture of MIPS. We are not going to go to the details, but so as I said, MIPS in its name has the word pipeline for P here. Pipeline means that these steps that are fetching instruction, decoding it, and executing it will be executed in parallel for several instructions. This will help the processor to speed up a lot. So it means that, for example, when an instruction is being executed in ALU, another execution will be fetched at the same time, because reading the instruction from memory can be done independently from the computations in ALU. And at the same time, also another instruction can be decoded. So you see all these are happening in parallel, so this will speed up the processor a lot. And then the instructions will proceed in these steps sequentially. So first each of them is fetched, then it is decoded, then it is executed, and then the results is stored in the memory, and then the next one arrives. And so it is preferable to have all these steps activated at the same time if it is possible. Sometimes for some instructions it is not possible, but this will be done as much as possible to speed up. So as you see, ALU is a very important part of the CPU, but it's not all of it. There are other parts. For example, we have the registers that are part of the CPU. We have all these decoding and fetching and stuff that are also parts of our CPU. So MIPS is a kind of processor. Where is it used? So it is mainly used nowadays in embedded systems. Embedded systems are computers that we see, are small computers that do a specific task and exist in many different devices. For example, home appliances, for example, microwaves, refrigerators, or cars, etc., etc. These computers have less power than our personal computers. So they usually have a simpler processor, a simpler operating system, smaller memory, smaller capacities, and they are for a specific task. As opposed to our personal computers that are much more powerful, and they are much bigger in size and can do many sort of things. Historically, MIPS processors were used even in personal computers and server computers and video game consoles. But nowadays, usually other processors, other more powerful processors are used. And so we want to learn how to program MIPS, but we don't have access to that, because if I want to program a MIPS processor, I don't have it on my computer. Then how am I going to do this kind of programming? So for this purpose, we are going to use a simulator called Mars, which simulates kind of the behavior of MIPS and shows exactly what would a MIPS processor do. And it also gives us an IDE or development environment as we're using for Python. It's something similar. So it gives us an environment to code and to execute the code and to see the results also, and to see how the register value is, how the memory is, and it also gives us the possibility to debug our code, meaning that helps us to find the problems in our code, if there is any. And it also has a lot of help with all the instructions that are in MIPS that we can use, etc. So here I'm going to show you this simulator. So it comes as a Java file or .jar file. I have uploaded it under module 5. You can download it, and first you need to install Java. I have explained a little bit the instruction steps in the assignment description. You can follow that. So as soon as you have installed Java, then you just need to double click on this file. So its font is very small. I tried several different ways to make it bigger, but I even checked different forums and people who had the same problem, but I couldn't manage so far. So I am going to use a magnifier to show you better how it looks. So you see here, so we will see how we can open a file and do our assembly programming, etc., etc. And then when we execute it, we will see that it actually shows us all the registers that exist. These are the list of all the registers that exist in a MIPS processor. They are very important. We're going to talk a lot about them and use them. So these will actually store all the data that are used in our instructions. And we will see that it will help us to execute and see if there are some error messages, and if there is some input output, we will see them also in these tabs. So let's close the magnifier and go back. We are going to talk a lot about how to use Mars, and we will see several examples during this lecture to how to do assembly programming with different instructions, so that it makes you easier to get the concept and be able to do your programming. So before we go to assembly programming, let's see what is there in MIPS memory, because we are going to use it a lot. So in MIPS, we have an architecture which consists of 32 bits. Nowadays, most of our computers are 64 bits. So MIPS is kind of smaller processor. It has 32 bits, meaning that it, for example, the registers in it are 32 bits long, and the instructions in it are also 32 bits long. And it is interesting that it has also 32 registers. So a register, as I said, is a cell of memory used to store data during the computations, because a processor cannot directly access the main memory of the computer to use its data inside there for its computations. The first step is always to load them in a register. If they are in the memory, they need to be loaded first in the registers. So registers are part of the CPU or processor, and they are the fastest and the most expensive memory in your computer. So there is only a limited number of them, and they have very specific use. We will see what are their uses. So here is the list of the registers in MIPS. We already saw them also in Mars simulator here. So here you can see also their list. So let's see what is their purpose. So there is a register specifically used to show zero, and it is also called zero. So there is a dollar sign at the beginning of the name of each register, and then they have a specific name that cannot be changed. And each processor has its own specific set of registers and its own specific names for them. So here in MIPS, we have a register called zero, which stores value zero, and it cannot be changed. Because in many computations, you need zero, so it is smart to have a register which is always zero. Then you don't need to each time load zero in a register and then you use it. So you have it already. And then there are 4 registers called A0, A1, A2 to A3 that are used for passing arguments to procedures. So in Python, you saw we were programming at a very high level. We could pass any argument we wanted with any name that we wished and with any order, etc., etc. Here we are much more limited. So whenever we want to pass some data to a procedure, we cannot just use it as we want. We have to, before calling the procedure, write our arguments in some of these registers. If we have, for example, one argument, we write it just to A0. If we have more, we might also use A1 and A2, etc. But we cannot have all the freedom in high-level languages. And then later on, when the procedure is called, we can go to those registers that we know are used for the arguments and then use the content. The registers from T0 to T9 are used to store temporary variables, so T for temporary. So for example, when you call a procedure or function, then you are doing some computation there and you need to store the results that you have computed so far temporarily in some register and then maybe use them again to calculate some final value, then it is preferable to use these registers. For example, maybe you want to sum several numbers together. First, you want to calculate sum of each 2 of them, store them temporarily, and then sum them up together later on. Then you can use simply these registers. And then we have also 2 registers called V0 and V1, which are used to use system calls and procedure return values. So return values in Python, for example, were easily returned by using the return statement. But here, we cannot return any variable we want and with any name that we want. We have to store our return values in these 2 registers. And then when we go back and the function call is finished, then the caller function can use the values that are stored here to see what was the result of the function that was called. And we'll also see that they are used for system calls. System calls are a way for MIPS processor or any processor to ask some requests from the operating system. We will see more about them because some operations in a computer can only be performed by the operating system, and MIPS or the CPU in general is not allowed to do them. So then the system calls are used for that purpose. We have also registers from S0 to S7 that are used for local storage, and the procedure that calls another one uses these registers. And there is a special register called RA, which stores the return address. The return address means that, so imagine you have a function called A, and you're going to call another function which is called B. After you finish executing B, you are going to return to some instruction. But how should you know to which instruction you are going to return it? That is actually stored in this register. So then in time of returning, your processor will check the address which is written here to know which instructions it needs to go back to. So here it says which registers a caller function can use and which registers a function that has been called can use. For example, a function that has been called can use T registers, as I said earlier, from T0 to T9 to store the temporary variables, and also V registers to store the return values. And the caller can use or must use A registers to store the arguments to the function. So let's see a little bit about MIPS memory. So besides the registers, those 32 registers that exist in MIPS, there is a memory, a RAM, that has 32 gigabytes of memory. And in memory, the instructions are used. So whenever you write a program, it will be stored first in memory. And then the instructions will be fetched from there and moved to maybe registers and then executed. And in memory, there are also the data, other data that you need for your program. For example, the variables that you have declared in your program are first in the memory, and then in the execution, whenever needed, those data will be fetched from the memory and stored in registers. So the data which is stored in registers is very temporary. Usually it has only, because the registers are very small and limited, they only store the data which is currently being used in your computations. And as I have said several times in this lecture, memory or RAM in a register is slower than register. RAM in a CPU is slower than registers. And the smallest unit of storage is 1 byte. Sometimes when you have small data, for example, an ASCII code that shows a character, you just need to occupy 1 byte. Sometimes you need to, for example, for storing integer variables, you need to occupy 4 bytes. So this is something we need to keep in mind when we are using assembly instructions, because there are in general different instructions for working with 1 byte or 4 bytes. In Python, it was not like that. So whenever we wanted to, for example, compute something, we didn't care at all about what was the size, because the interpreter in the Python code was smart, and it would generate a code which was correct, and it would guess the size of the data that we are working with. But here we have assembly code which is not that smart, and we have to take care of the sizes ourselves. So in MIPS programs and also in MIPS processor, we have the notion of text segment and data segment. So text segment simply means the program that you have written in assembly, the set of instructions that are going to be executed. They will be stored in a different place, a specific place in the memory. And we have also the data segment, which will store all the data that you have defined. For example, the variables that you have declared in your program, they will be stored in a separate part. And in your program, we will see that we have a data part and this text part. And in Mars, we will see this more clearly. It shows us which part in the memory is data segment and which part is text segment. So now let's go to the assembly programming. So each assembly instruction in MIPS has 32 bits. and consists of several parts. The first part is called opcode, which is always 6 bits, which is the instruction. For example, it is add or subtract or load or store. Things like that are called opcode in assembly programming. And then after the opcode, we have operands, which are the data that you are going to work with. You're going to do your calculation on. For example, the data that you are going to sum up together or subtract from each other, and so on. And this data can be either stored in a register or can be immediate, meaning that they are a constant that you directly write. For example, you write add, register, blah, blah, and 100. So this 100 means immediate. You cannot use, for example, variables. Keep it in your mind. This is very important. You cannot use variables directly in your instructions. You can only either use registers or immediate values. So we have 3 types of instructions in MIPS. The first type is called R type, which is mainly used for arithmetic and logical operations. And what is specific about them is that they only use registers as operands. So here you can see that the operand is 6 bits, and then it is followed by registers that contain the data. This details is not important. I just wanted to give you a brief overview of what is happening there. So then the next type is called I-type instructions that can have as operands both registers and immediate. So here in this case, again, the operand is 6 bits, and then comes the registers and maybe the immediate. The immediate value here in I-type instructions can only be 16 bits. So if you have immediate value, which is an integer, for example, and it needs 32 bits or more bits, then actually it has the instruction has to be broken down to several steps. We are not going to go through its details, but it's just interesting to see that how much freedom we had with high-level programming that we just don't have simply in assembly program. And we need to think a lot in assembly programming to limit the number of operands so that they fix in operations, because there are 1 or at most 2 operands in every instruction. You cannot have the freedom of summing up as many numbers as you want at once. You have to break it to several instructions. The last type of instructions are J-type. We will go through many examples of these instructions and see how they work. But so briefly for now, J-type instructions are for jumps in the program. For example, imagine you want to return from a function that is being called, so you need to jump to your previous place. These are called jump instructions. So they have an operand which says what kind of jump you should do, and then the rest is the address that you're going to jump to. So the execution has several phases. So first, the instruction needs to be loaded from the memory. For example, imagine here we have an instruction that says add I. I is for immediate. Add I, and here it means that the data inside register T2 will be added by the value 2, and the results is going to be stored in register T1. This is what we understand, but the computer doesn't directly understand that. So after loading this instruction, it will actually decode it to machine code. So then this opcode is actually translated to this code. So for every specific opcode, there is a specific binary representation. And this is the same for registers as well. So every register has its own binary representation, which is unique. And then the immediate value is simply here the binary representation of 2, which is 1, 0, as we have learned in previous lectures. So you see here exactly how a machine instruction looks like in a machine language. So you can see how difficult it would be to directly do machine language programming. It is, I mean, chaos. So assembly programming is a bliss compared to this. And then after the coding, we have the execution phase in which this instruction will be passed to ALU, for example, and then the actual transitions will be done in the circuits that are in ALU. And then if there are any results that need to be stored in memory or some register, etc., will be done at the last phase. So here you see an ALU. It takes as input some registers, for example, and it also needs to know what is the operation, what is the operand, and then it will store the result. This shape that you see here is like some sort of a rotated V shape. It's usually universally used to show ALUs. So ALU is a very important part of the processor or CPU, and it is essentially an electronic circuit which carries out the logical and arithmetic operations. And it is used to calculate different values, for example, to sum up some numbers or to multiply, and also to calculate jumping addresses, because sometimes the jumps do not specifically say what should be the address. Some calculations need to be done. For example, what is the current position and how far is the destination, and then these two values will be summed up together to calculate the destination address. And ALU can do arithmetical and logical operations, and those kind of operations that we had seen so far, for example, and, or, XOR, etc., are all done by ALU in the computer. And then it can also do comparisons. For example, is this number smaller than the other number, or equal to it, or not equal to it, etc. All these that we had been using before, but we didn't know that where they are implemented are actually implemented in ALU, which is inside a CPU. Now let's see the assembly instructions. So besides actually assembly instructions, there are something called assembly directives, which are some sort of instructions still that tell the assembler to perform some task or change a setting. For example, they tell the assembler to declare some variable. Declaring a variable means that we reserve some space on memory for that variable. For example, if we have an integer, we need to reserve 32 bits for it. If we are declaring a character, we need to reserve 1 byte or 8 bits for it. Or if we have a string, we need to calculate based on the length of the string what value need to be stored on memory. So this reserving space will be done by assembler. So let's see what are these directives. So .data is an assembly directive which is mark beginning of a data segment. So as I said earlier, we have data segment and text segment in MIPS assembly. In data segment, it is a part of your code in which you are going to define or declare your variables. In order to show the assembler where is this part in our code, we simply write .data in the beginning of that. We will see shortly an example about it. So first, we start by .data, and then afterwards we will declare the variables that we want. For example, here a variable is declared which is of type of ASCII Z, which is essentially it means that it's a string which has ASCII characters. So for declaring that, first we have to write dot ASCII Z, and then it must be followed by the actual string itself. For example, imagine you want to print something on the screen for the user. You need to first come and define it like this in the beginning of your program and then later use it. You cannot declare variables in the middle of your program. You don't have that freedom that you would have in Python, for example. And then if you want to have small values that are stored in 1 byte, you can use dot byte. And the dot word here means that be your values that occupy 4 bytes or 32 bits. So you see different instructions are used for declaring variables of different size. And after you have defined all the variables that you want, you need to use dot text, which shows the beginning of your program. And I should mention something, that whenever you use dot byte or dot word and you write a list of numbers, this will be treated as an array. So an array is a list of elements that are stored one after another in memory. We will talk a little bit more about them later. So here I have an example. So here you see that we have a program that in its beginning, we have our data segment. It doesn't need to be in the beginning. Data segment can be at the end as well, but it has to clearly be marked with dot data directive. And after that, here we have just declared a string. So hello is its name, and it is followed by colon, and then we have the directive dot ASCII Z, which shows the type of this variable, and then the value for this variable is specified. And in case of strings, we need to put them inside double quotations. So I didn't need to declare any more values here, any more variables here. So I decide that, for example, my program is going to start here. So I have to use dot text directive, and then my program will follow. In this case, the program is empty, for example, but we will see more meaningful examples in the coming slides. So now let's see about system calls, because we are certainly going to use them in any program that we write. So these are predefined routines in Mars or any CPU has them. System calls will always be executed by the operating system. For example, it can be Windows on some machine or Linux on another machine, etc. But this will be only executed by the operating system, because they are usually sensitive instructions that only OS has the privilege to execute them. For example, they are usually used to access the hardware devices or the logical entities on a computer that might be sensitive. For example, the files in a computer, etc., that they just can be reached with an operating system. CPU directly cannot access them. So it always has to ask the operating system. Says, could you please open this file for me? Could you please write this sentence to the screen for the user? So the control is somehow passed to the operating system for security purposes. And each system call has a unique number. For example, for printing integer, there is a unique number. For printing a string, there is another unique number. For opening a file, closing a file, etc., etc., there are unique numbers. And before calling the system call, the number specific to that system call needs to be stored in the V0 register. So we need to know what are the codes for different system calls. We can easily find them, for example, in Mars help, or we can just simply Google them. As soon as we find them, we need to store them in V0 register, and after that, we can use system calls. And for system calls, there is an instruction called syscall that we use, and we will see it in an example. So system calls are used for, as I said, printing, reading, opening a file, exiting, reading from a file, exiting the execution of the program, closing a file, etc. And you can find all of them in help of Mars, or you can read about them online. And these are some of the popular system calls. For example, print integer, print floating point, print a string, and exit. Exit is something we always need at the end of the assembly programs to exit safely. And they have their own limitations. For example, when you want to print an integer, so its code is 1, you have to load it in V0 register. And also the value that you want to be printed out cannot be anywhere. It has to be stored in A0 register, as you see here. For example, if you want to print a string, which happens very much in programs, you need to load value 4 in V0 so that the operating system knows which system call you are using. And then the string that has to be printed out needs to be stored in A0 register. Remember, A0 to A3 registers were used for passing arguments to functions. The system calls are some sort of function calls. So we pass their arguments by this A0 register, for example. And exit doesn't have any arguments, but you just have to load the value 0 in V0 register. We will see exactly how we load values into registers. So the assembly instructions have different forms and different uses. For example, we have some instructions that are used to transfer data to and from memory. We have arithmetic instructions, logical instructions, jump instructions, which are some unconditional jumps. And we have also conditional jumps. And we have also pseudo instructions. So let's see one by one. So data transfer or memory access instructions are used to read something from memory, for example, in this case it is RAM, and store it in some register. Store instructions are somehow the opposite. You read something, for example, from a register or immediate, and store it in memory. So here there are some examples. In the first line, we have LI, which stands for load immediate. Immediate means a constant value that you directly write. In this case, it is 100. So this instruction is saying load immediate 100 in register T1. So immediate, yeah, as I said, is a constant value in the instruction. So this will load it in this register. We can have loading from other registers. So when we want to copy some value, we use something like this. For example, this is saying load byte. So it means that it will only load 1 byte. And from where should it load? So the address is set here. This is interesting here. So please pay attention a little bit to here. This is saying the address of the data is stored in register T2, and this 0 value besides it says the offset, or says the difference from the address here. So in this case, it says, go fetch this address, sum it up with 0, you go to a location in the memory, and then load that value into register T1. These are used in cases when we don't have the data in some registers, they are rather on memory and we need to access them. So first, in this case, we need to load the address of the data in some register and use that register to help us find that data in the memory. So instead of 0 here, we can have, for example, 100, which means go fetch this address, sum it up, read 100, you will reach some location in memory, read the data from there and store it in this. So then after load byte, we have load word here. Word means simply 4 bytes of data. So word is 4 bytes. Byte which is used here is obviously just 1 byte. So here we have 4 consecutive bytes in a word. So it will go to this address associated into T2 plus 0 and load 4 bytes of it in T1. So these sizes are very important. So whenever you have a piece of data which is just 1 byte, if you use LW instead for loading it, you will most certainly corrupt your program because it will read not just 1 byte from memory, it will instead read 4 bytes. So it will actually load a different value to your register. So your calculations that are based on that value will most certainly be wrong. So whenever you are programming assembly for your assignment and you see that there are problems in your code, check all the sizes in your instructions and your variable types, etc. These are very important. So let's. So here I have just listed some example. You can you can check the long list of instructions in Mars Help, or you can Google it. And in our examples, I have written specific registers. These are again just for sake of example. Here, instead of T1, we could have, for example, A3 or V1 or most of other registers as well. So besides loading, we have also store instructions. So here we store 1 byte, and with SW we store a word or 4 bytes. So this first one says go to this address and store in it the content of T1. And we know that the registers are 32 bits, but here we are just going to pick 8 bits of it. Which 8 bits will it be? It will be actually the lowest 8 bits. So these are very important in your calculations. So whenever you just load 1 byte to a register, it will be stored in its lowest 8 bits. And when you store just 1 byte from a register, again, only its lowest 8 bits will be used. So now let's finally see an example. So you remember we had a hello world example in Python, and it is classical that whenever you want to start programming in a new language, you first try to print hello world. This is the simplest program that you can write, and you see that it is working correctly. You can have, for example, a simple program that just adds 2 numbers, but as soon as you don't print it, you usually don't see or feel that it's working correctly. So here we have the hello world example in MIPS assembly. Let's do it together. So I come here to Mars and I use my magnifier. So I come to File, press New, or I directly use this button. So I would like to minimize this. Okay. So I want to print hello world, which is a string. In Python, it was very easy. It was just one statement to write your hello world program. You would simply write print, and inside parentheses, you would write hello world, execute, you are done. But here we have a few more steps. So first, we have to declare a variable that contains the string that we want. And for declaring the variables, we need to use a data segment. So I press tab and write data, you see when I am typing, I have many helps. For example, as soon as I type dots, it lists for me all the directives that are that can be used with MIPS. So I write data, and notice the color change. This is important and helpful that you notice the different colors that are used in your program, because when you misspell, you will have black. But when you spell correctly, you will get the correct color. So this is also some help. So I want to declare a string. First, I need to give it a name. So I go back, give it the name hello, and then I need to use a directive to specify its type. So it's a string. So we will use ASCII Z, which means a string which is terminated by 0. Always we need the strings to be terminated with 0. So we will always use this. And then I press space and use double quotations and write my string. Okay, now I want to print it. So I need to start my program. And for starting my program, I need to use the text directive to let the assembler know that the rest is my program, not anymore data variable declarations. So here I need to have a function called main. And inside my function, I want to print. So for printing, we have to use a system call. We cannot directly print here. Even in Python, when we write print, a system call will be called underneath. We just don't see it because we are programming at a high level. But here we are at a low level, so we have to call it directly, the system call. We have to call it directly ourselves. So remember that we need to load the type of system call in register v0. So let me just write it as a comment. Load the syscall type in register v0. Okay, so I need a load. So what kind of load should I use? Should it be, so we saw we could have li, we could have lw to load the word, we could have lb to load the byte. And when you write their names, you will see some help here. So here I want to actually write or load value 4, which is used for printing integer. So I have an immediate. So I have to use li. I don't have any other choice. Li stands for load immediate. So it tells me that after that I need to write a register, comma, my value. So the register in this case must be v0. I don't have any other choice because I'm going to call a system call. And then I need to write comma and then my value, which is 4, because printing integers has the code 4. I don't have any choice in this case either. I move to the next line. Okay, now I want to specify what will be printed out. So I will load, but what am I going to load here? So I have here some variable that I want to use. This variable is stored in memory. This needs to be copied to some register. So for this purpose, LA is used, which means load from some address. And what is this address? The address is actually given by this variable name. So I write it here. And where am I going to load it to? Because I'm going to print, as I said, for printing, the value needs to be loaded always in A0 register. So load the value or the string to be printed. Okay. And in the next line, I am going to call the operating system with using syscall instruction. So it issues a system call. These hints are very helpful. Okay, now my program is finished. I come here to the run, and maybe before that I need to save my program somewhere. So I create a folder here, or no, just let's have it. Okay. Now I come here. I need to always press assemble or F3. I write it. It will give me if there are any errors, etc. So now I have been actually moved to a new tab called execute. Previously, I was in the edit tab. And in edit tab, if I am editing several files, all they will be listed here. But now, after calling run, I will be moved to edit, to execute tab. Here, there are lots of interesting information. So here we see our text segment, which shows what our program is. So you see here all the lines in my program after the .text directive, not before that. So I had the main function in the first line, I had this instruction, and then at the next line I had another load instruction, and then I had syscall. And very interestingly, you can see what is the machine code for these instructions. So you see here, this is the machine code. So imagine we would want to do the machine language programming. We had to come up with all these numbers. 0x means that this is in hexadecimal. So there are 4 instructions in machine language, and it is even written where they are stored in memory. So this first one is stored at 0040000. The next one is 4 bytes later, because remember each instruction is 4 bytes or 32 bits. This is interesting to see all these details here. Where are the instructions stored and so on. So this was for the text segment. Now below that, there is the data segment, which shows how our memory is formed. So you see our memory is mostly empty. It has 0 all over the place. It is, but because we have our string, there are some places in the memory that have some values. This will help you a lot later on when you want to do your own assembly programming and you want to debug it and see what the problem is in your code. You can see what values are stored directly in the memory. So for example, in this case, I had a string. So each string is a set of characters which will be followed one after another on the memory, and each character is 1 byte, and each byte is shown in hexadecimal with 2 values. So for example, I have here one of my characters which has the hexadecimal value in ASCII system, which has a value of 48. Another one is 65. Another one is 6C. Another one is 6C, etc., etc. So these are all my values in the string, and then the rest of the memory was not used by us, so it is 0 because we have a simulator. If it was a real processor, all these cells would not be 0. They would have other values because different programs would be using the CPU for different purposes, so they would have been written to, but in this case, they are 0. And below this, I have the messages that Mars is giving me. For example, it is saying that the assemble operation was completed successfully. Otherwise, if there was any problem, any error, it would be shown to me here. And in the registers, interestingly, we can also see the values. So you see these registers were not used, so there is basically value 0 on them. And the PC here, or it shows the program counter, meaning that which line in the program or which address is used for executing. We don't want to go to its details, but we used A0 and V0, but they are shown 0 here because the program is not running yet. So we have just assembled the code and we have not yet run it. So let's run it now. Now when we come here in this toolbar, we have two options for running. First is this button, which will run all the program, or it will run it as much as it can. Maybe it hits an error in the middle. It will stop as soon as it cannot continue any further. And we have another option, which is also very interesting for learning and also for debugging, which will execute one instruction at a time. So if I click on it, it will execute the first one. The next one is highlighted, meaning that this is the next thing that will be executed, but it is not yet executed. And we can now, this is what I love about it, we can go to this V0 and see its content because we aimed to load 4 into V0. Was it done correctly? Let's see. So we go to V0. Yes, it was loaded correctly. So this helps you a lot. And then let's click again. So now this second instruction was also executed. So we assume that the string hello is, the string that is stored in address specified by variable hello is stored in A0. Now let's see the content of A0. It is still 0 because we will see why. So this instruction was actually translated by the assembler to two smaller instructions. So these are the real assembly instructions. And these instructions that we write are sometimes pseudo instructions. We will talk about them more. So they are even a little bit at a higher level. So here, instead of load A, the assembly is actually using two smaller instructions. So let's click it again. Now let's check the content of A0. So A0 has now this this value which is loaded to it. And then the system call will be executed. Now we should see the output on the string. The string is actually here in run.io. So you see the string was printed out correctly. So let's see if I can have some error in my program. For example, let me drop this. Now let's run it. What happens? So you see it doesn't complete assembling, and it highlights this part and it is giving me some errors. So it says error in some specific line, column, some specific column, and it is complaining that something is not correct, and it shows me some examples that maybe you wanted to write something like this. So when I click on it, the line of code that has a problem will be again highlighted, and I should try to fix it. So you will always, you should always use the error messages to find where is the problem, but not always the error messages help you. Sometimes you don't have any error because the syntax is correct, but there are some other problems in your program. Maybe, for example, you used wrong sizes for your instructions, or you loaded wrong value, or you used wrong address. These are things that are more difficult to debug, and as hints, you can always use for example, data segment or registers. In this case, they are empty because the program couldn't be assembled. But once it is assembled, you can use the one-step running to debug your code. Now let's go back to our slides. No, not here. I should first close the magnifier. Yes. So we saw already this example. So the whole string will not fit in just one register because it might be very long, even in this short string. Not all of it can fit in just 32 bits. So the address is already loaded in A0 register. So we have seen so far different directives and also load and store instructions. Now let's see how we can do arithmetic and logical operations with MIPS. All arithmetic and logical instructions have 3 operands, and their order is very important. We cannot change that order. We always have to see the instructions and follow them. So first we need to write the opcode, for example, add, multiply, etc., followed by space or tab, followed by 3 operands that are separated with commas. First, the destination is written. It is a bit counterintuitive, but this is how it is. So the destination is the place you want to store the results. And it always has to be a register. You cannot use a variable. For example, you cannot write A is equal to A plus 1, where A is a variable. No, this always needs to be a register. And then we have the left operand and right operand. So for example, in Python, you would simply write variable A is equal to variable B plus variable C. But in MIPS, you cannot directly use variables. So you have to first load them in some registers. Imagine they are used in S0, S3, S2 registers. So then for adding them, you will write add instruction. And then first you specify the destination register and then the right-hand side and left-hand side operands. So for telling which data you want to use, you need to give the address of it. For this purpose, you either use registers or, as we have seen so far, for example, you say my value is stored in register S0 and you pass it. Or you use immediate values, immediate addresses can be as well, or you use a label. We will see how we can use labels. For example, when we were printing hello, we were using a label. These are called labels that are written in the beginning and then are followed by colons. So here we have a label that gives, that is used for a variable. In line 13, we have another label, which is used for marking a specific line of code. They can be used, for example, to mark the beginning of a function. So now let's see some examples on arithmetic instructions. For example, we have add T1, T2, T3. So it means that store in T1 the value of T2 plus T3. Subtraction and multiplication and division are similar. And these two, add I and sub I, mean add immediate. So instead of adding 2 registers, we have here 1 register and 1 immediate. And we don't decide where the immediate can appear, where the register can appear. All these are fixed in the MIPS processor, and we have to just follow the instructions. So you remember that the instructions had different formats. Some were called R-type, some were called I-type. In R-type, we only use registers like you see here. So these instructions are called R-type. In these two instructions, we have both registers and immediate, so they are called item. Let's now write an assembly program that increments a variable and prints out the result. So you see comments start by hashtag in assembly. So we want to increment a variable and print it out. Print out the results. It's always good that you add a lot of comments to your assembly code, because as you have seen so far, the assembly code is not as intuitive as high-level programming. So you will simply forget, even if it is your assignment that you are doing, it is important for you, for your sake, that you comment it very well, so that next time that you are going to work on it, you remember what you were doing. So I want to have a variable. So I first need to have a data segment. Then I will give a name to my variable, for example, n. Then, so I want it to be 32-bit integer. So I define it as a word and I assign value 10 to it. Then I want to print out at the end a string on the screen and followed by the value. So I need to declare a variable for that. So for example, string, which is a string, and it says the result is followed by the value. Okay, these are the variables that I need. So now I need to start my code. So don't remember to add the text directive. So here, so I have the variable which is stored somewhere in memory. Before I increment that, what do I need to do? I need to first this variable first load this variable to some register. So here I start my main function. Main is classically used in programming. For example, in C programs and C++ programs, it is compulsory to have a main function from where your program starts executing. In assembly, it is not compulsory, but you can still have it as a starting point. And in Python, for example, you could have a main file from which your execution starts, but it was optional. So here I would like to have main. So first I need to load my variable from the address. Labels are like addresses. So I use LA, which loads from some address. And then here are some hints for me. So the destination you see always has to be a register. So I want to, it is temporary. So I use a temporary register, for example, T0. It can be any other temporary register. The last one is T9, I think. So I load AU N1, or it's called N, to this register. Then I want to, so far, what it does is that it loads the address and gives us the address. It loads the address. This is very important. This is not the actual value of n. So T0 at this point contains only the address. The next step to use this address to load the actual value. So I use LW to load the actual value to some other register. For example, it's because I want to later on print out this variable. So I can use another temporary register. So here I want to load a word from some address. I know the address is stored in register T0. And I don't want to go anywhere beyond that. I want the address to be exactly the one stored at T0. So I will write 0 before. This 0 is the offset. For example, sometimes you have an array. So you know the address of the beginning of the array, but then you want to fetch some element later in the array. So then you would use some offset, for example, 100 or 4 or something like that. But here I know exactly the address of the variable. So I use 0 as offset. And then I can increment. So for increment, I want to use 1. So I want to increment my value by 1. So I have an immediate value. So I should use then add I. My destination, I would like to be T1 itself. And my source, one of my sources. So you see here, the first source is always a register. So I want it to be T1 because I want to increment that value. And my immediate is 1. So now I have calculated what I was looking for. So I want to now print out the results. So for printing out, remember, I need to first load the syscall number. So for in this case, I need to use li because I have an immediate value and I have to always store it in V0 register. I very much recommend that you do these steps at the same time as you are watching to this video, because otherwise you will not remember all the details. You have to do it your own, execute it on your own, and then see all the errors and so on and experience, because you learn programming only by experience. Watching videos is not enough at all. So continuing, so I have to load 4 for printing strings. Printing strings. Then I need to load the address of the string in register A0. So load A, which stands for load address. I use A0 because it is the argument for the function that prints strings. I cannot change it. And the address is the string called str. Then I call syscall or issue a system call. So when a system call is issued, then the operating system will see that it is number 4. So it is essentially printing a string and it will print it out. And I also want to print our results afterwards. So again, I use li, but this time I use number 1 because number 1 is for printing integers. So this is for printing integers. And then I need to load the content to the value, the integer value that needs to be printed out to register A0 again. So I will not use li because the value is not immediate, and I will not use la either because the value is not in any address. I cannot even use load word to copy my result, which was in T1 register to A0 register, because if I press space, you will see that although the destination in load word can be a register, but the source cannot be a register. So a trick is to instead use add instruction. So we add with zeros, basically. So the destination is A0 for printing. The source is T1. And the value we want to add with is register 0. So we will add 0 with T1, which is T1, and then store it in A0. And after this, I can have a syscall. So when issuing this syscall, the operating system will realize that it has to print an integer and the value is in A0. So now let's run it. I use my magnifier here. So we come to run. I have to first save it. So let's call it increment. Okay. Run, assemble. So we have all the code here. I just I press this button so that it executes it all. So we didn't have any issue for assembly. So you see, it could assemble successfully. And now we want to run it. So let's see the result. So it is saying hello world. This is the previous output. I should clear here, run again. Assemble, run. So it says the result is 11. But after that, it has some sort of error because I didn't use exit syscall at the end of this program. So let's remove it. So I should go here for exit syscall. I have to load value 0 into 0. And then I issue syscall. It doesn't have any arguments. Now I do run, assemble, and execute. Now I have an error. So the problem was that I had used a 0 code for exit syscall, which was not correct. The actual code is 10. So now let's run it and see the results. So the assembly part is done. Now execute. And you see it says the result is 11 and program is finished running. This is not part of the program. This is part of the execution that writes this sentence whenever the execution is finished correctly. So now let's close the magnifier or disable it basically. Let's go back. So we have seen this example. Now let's move on to logical instructions. In logical instructions, again, we have 3 operands, similar to arithmetic instructions, and it has the same format. So first, we have the opcode, then destination, followed by left operand and right operand. So let's see an example or several examples. So we have here in logical instructions and, or, XOR, etc., which do the operations on registers only, and they are R-type instructions. But we can also use immediate only for the for the right-hand side operand. So for that purpose, we use add I, in which I stands for immediate, or I, XOR I, etc. So for example, in this case, we do bitwise AND, meaning that we take bit by bit these values, either being in T2 register or whatever register, and in the immediate, and we perform the logical operation, which is AND, and store the results in register T1. There is a shift operations among logical operations that are very interesting. We use them even when we had Python programming. They are used in programming when you want to move the shift to right or left. Shifting means moving. So you can shift the bits by 1 position, 2 position, whatever the size allows you. So for example, if you have 32 bits, you can shift 31 or 32 times. So this is an example. This says take the value in register S1, shift it 10 times or 10 positions, 10 bits to left. So S stands for shift, L stands for left. And shifting to left will multiply by your number by a value which is 2 to the power of the number of shifts. So here, this will multiply your value by 2 to the power of 10. Right shifting is the opposite. So if you shift to the right, it will divide your number by such value. For example, if you shift 1 position to the right, it will divide your value by 2. You can try it with some examples on paper to see why this is the case, why moving bits to left and right is like multiplication or division by 2, or a number in power of 2. So we saw that as immediate, we have only space for 16 bits in I-type instructions. But what if we want to use bigger numbers? So here we have an example. So for example, add I is an instruction which adds with an immediate. And as we have seen so far, so in this case, 6 bits is used for opcode, which is add I, and at most 16 bits or even less is associated for immediate. So for this purpose, we need to use more instructions than just one instruction to be able to do this sort of calculation. So in this case, we have an example that we can see. So imagine we have a number which is larger than 16 bits. So 2 steps can be taken. The first step is to use a load immediate. So here, for example, the value being 100 is loaded into register T1. And the next step has a use OR immediate. So you see 100 here, or any immediate that is used here can be only as big as 16 bits. When it is loaded into the register has 32 bits. So 16 bits are empty, basically, that we can fill up. To use those bits and fill it up with more bits that correspond to our big input, we can use the OR instruction. We can use OR with immediate. Because those bits are left as 0 when we OR with some other bits, it is like writing those bits to the register in the empty places. So for example, imagine now we have this value which is written in hexadecimal. 0x in the beginning of a value means that it is in hexadecimal, which essentially means base 16 numbers. So we want to store it in register T0. So in this case, we first load the first half, the higher half of the number, which is corresponding to these digits here. In decimal, the value for it is 4,112. So we first load this part to register T1. So then at this point, register T1 will contain 1010 and the rest is 0. So we couldn't load the rest because they couldn't fit in our instruction. It will be beyond the size of instructions, because remember that each instruction can only be as big as 32 bits. So then we need to use an OR instruction to do bitwise OR on T1 and another 4,112, which is the rest of this number. In this number, the first and second part were the same, but this is not usual, of course, the case. But whatever is the lowest half, we have to do bitwise OR with that, with the higher half, which is stored in T1 register, and put the result in some register. For example, in this case, T0 is selected. So you can see that in binary or in hexadecimal, you had 1010 in T1 register, and in your immediate, you had 00001010. So all these being, if you use bitwise OR on these two numbers, the result will be 1010101010, because when you do OR 0 or 0, the result is 0. When you do 0 or 1, the result is 1. and so on and so forth. So the empty bits will be filled up with the lowest half of the number. So there is a notion of endianness in processors. A processor can either be big endian or operating in big endian mode or little endian mode. Big endian and little endian describe how data is stored in memory, how bytes are ordered in memory. In big endian, the most significant byte of the data is stored first in the memory. So if you look at here, so imagine you have a number which has 4 bytes. So first, the highest value byte, which is the one to the left, is stored on memory. And in the bigger address, which comes just after that, you have the lower part, because you know in hexadecimal or binary or decimal representation, as we continue from left to right, the value is decreasing. So in big endian, the highest value digits are stored in smaller memories. So in little endian, it is the opposite, meaning that the lowest parts are stored in lower memories. These are the addresses. Imagine it was A, for example. And then when you proceed in the memory, you will store the higher bits. So MIPS can be used in both ways, little endian and big endian. The big endian and little endian do not specify how bits are placed in a byte. So in a byte, there is always the highest part on the left and the lowest part on the right. But they rather say how bytes are placed in the memory. So we have seen so far arithmetic and logical operations. Now let's talk about unconditional jumps in the program. You can use jumps to have function calls. There is no such thing as function call that is as it is in Python programming or C programming. You have to make it yourself to work by using jumps in the program. So for this, we have these popular instructions. There are other as well, but these are enough for this course. So for example, one is the J operation. After J, there is just one operand, which is the address we want to jump to. It can be a label. For example, you can write J main, meaning that jump to the main, or jump to some other function. You write its name. Or it can be an address. For example, in this case, 1000. Maybe you know the address of the instruction. In the memory, you can directly use that. And we have another instruction which is called JR. It goes to the address that comes to the register next after that. For example, it can be used for returns. So we know that we have a register that it is called RP, and it can be used for returning. It contains always the address of the place that we should return to, so we can use that with JR instruction. We will see that in an example. And JAL is used for calling a function. So then here you can give the address of the function or the name of the function for it to jump to. But the difference between JAL and J is that the JAL updates RA register, so it updates the return address. So the usual idea is that in time of calling a function, you use JAL. And then when you want to return from a function, you use JR, because in this case, you will update RA register with the return address. And then later on, you can return exactly to that address. Here, $1 means that some symbolic register. One is not the name of a register. You can, for example, put A1 or S2 or something like that here. So if you have several JAL instructions, it should be careful about the return address, because each time the return address is updated and you might not be able to return to your initial place. You need to care extra attention to this. So let's see how we can have procedure calls or function calls and return. So when we want to call a procedure, we want to simply break the execution. We don't want it to continue sequentially. We want to lead the execution to some other place in our program. So we want to jump or branch. So for this, we use JAL and followed by address. And this will update the register that contains the next execution, the address of the next instruction to be executed. So register RA stores, in this case, the return address. Because when we want to return from a function, we want to go back to the place where we were executing just before we entered the function. So that address is stored in RA register. So in time of returning, we use JR and followed by RA. So this will update PC. PC is program counter, or intuitively, it is the address of the next execution, the address of the next instruction that will be executed. So when you use JR followed by RA register, you will say that the program counter will be equal to the value that is stored in RA. So it will jump to this position and execute from there. If you want to pass any parameter to a function, you can only use registers A0 to A3, as we had discussed earlier. For example, we have already seen it when we want to print something. We had to put the value that was going to be printed out in register A0. This is the same concept in other functions as well. So when you want to have several parameters, then the first parameter should be in A0, the second one in A2, and so on and so forth. For functions that have more than 4 parameters or 4 arguments, other remedies are done because it is not simply possible. We just 4 registers, but we are not going to go to those details now. Now let's write a simple function together that reads or gets an input value from the user and returns it to the main function. So we go to Mars and I open a new file. So here we want to first define the variables that we need. So I need to have data directive here. So I want to ask the user for input. So I want to write a string that says enter your value, blah, blah. For this purpose, I define a string which is called prompt, and it is a string, so I have to choose ASCII Z, and its text should be, for example, enter an integer. And I put \n at the end to go to the next line. \n is used for going to next line. And I don't need any more variables, so I will start then my code. So I have a main function in which I will just simply want to call my other function so that you see how a function is called. So I define another function here that gets an integer from user, and in main I want to call that function. So I have to use gel, and then I give the name of the function here. In the next line, so after I return from that function, I don't basically I can print that value, but let's just store that value in some register. I will copy it to register S0, and I assume that it is the return value. So the return values are always either in V0 register or V1. So I assume it is in V0. So I copy V0 to S0, and I call afterwards the exit syscall. So for this, I load immediate value 10 for exit in V0, and I issue a system call. So that was my main function. In my get integer function, I want to prompt the user for input. There is a syscall for that, and before doing that, I want to write my prompt string on the screen. So I have to load its code in register V0. For printing string, I have to load 4. Then I call, now I have to load the string address in register A0. Then I call syscall. So first I am going, so this will print my string here. Then I want to ask for user input. So the syscall number for that is 5. So I load immediate to V0, the value 5. Then I issue a syscall. And after this, the value will actually be stored in V0, and I return that. So after this, the value is stored in V0, which is good because it will also be used in time of returning, so I don't lose that value. So now I want to return, so I use JR, and I have to use RA register because RA is updated when I used JAL. So basically after this operation, RA register will remember that the next operation to execute is this line, is line 6. So then here when I call JRRA, it will jump to line 6. So let's see if it works, or you might also get some errors. So let's call it prompt and run it. So we didn't have any assembling error. Now let's calculate, execute it. So it is saying enter an integer value. Okay, I print enter. The program is finished because I didn't print it or anything, but I could come here and print it. So let's go back to the slides. So we have seen so far jumps which were unconditional. They were unconditional jumps, but we can also have conditional jumps, which can help us to implement if statements or for statements, etc. In assembly, we don't have such a thing as if statement. We have to implement it ourselves by conditional jumps. For example, we have BEQ, which will only jump in case of equality. So it will branch or jump, they are the same. Branch if equal. And it takes two registers to compare with each other. And if they are equal, it will jump to the target. The target can be a label, in the program, or can be an address, etc. This one will branch if not equal. This one, for example, if will branch if greater than or equal. This will branch if equal to 0. So it will check this register and branch only if the value stored is 0. And this will branch if less than, this will branch if less than or equal. So we will see an example about that, but before that, let me introduce pseudo instructions. Pseudo instructions do not have a direct hardware implementation. There are some instructions at a higher level that are offered to us by the assembler that we can use so that assembly programming becomes easier. So you have already seen that I used move instruction in the previous example. This is actually a pseudo instruction. It is, so what it does is that it copies the value from some register to another one, but it actually doesn't exist really in the computer. So the assembler translates it to add U instruction, which adds with a register 0. I also used this instruction in an earlier example. So instead of using this, the processor will actually use this instruction, which we add 0 to register T2 and copy the result or write the results in register T1. In order to simplify for us, the move instruction is offered so that we can more intuitively use that. So let's see how arrays are used in MIPS. So in Python, you saw we were easily defining arrays, and we could easily define or access the different elements in the array by their indices. In assembly, as you can already guess, it is not that trivial. So we have to do some calculations for accessing array elements, for example. So first of all, an array can be declared in different ways. One of them is to just list the contents of the array. For example, here we have an array of bytes, which are in this case single characters, or in the second one, we have an array of 32-bit numbers. And for each array, we need, of course, a name and the type. And here we have the initial values. So vowels in this case has a length of 5 because it has 5 characters in it, and each of them is as big as 1 byte. So this array will occupy 5 bytes on memory, as opposed to power 2, which I will show is much bigger. So somewhere in memory we have 5 bytes allocated for vowels array, and they store these characters one after another. So 97 is the ASCII code for A. And then after that is ASCII code for E, and then so on and so forth until it finishes. And you see, this is stored, for example, on this address. Just look at the first digit. The first digit is 0 here. The next digit is 1 because each byte will increment the address by 1. And the last address here in the array is 4. The next empty place is at address 5, but we cannot use that to store the next array here because the elements in that array have 4 bytes each because they are words. Their type is word, so each word is 4 bytes. So when we define words, in memory, they will be stored at an even location. So they will go to the beginning of a block, basically. So for example, they can be either at address 0 or a 4 or 8 or so on. So here 0 is occupied, 4 is occupied, so they will come to 8. So the first element in POW2 array is stored here. So you see it occupies 4 bytes. Although its number is small, but it occupies 4 bytes because of its type. And the next element occupies the next 4 bytes, and so on and so forth. So if we want to access the first array at index k, we just have to add k to the beginning address. So these labels for arrays will show the address of the first element in the array. So vowels in the assembly program for the assembler would mean the address of this first cell. So when I want to access the ith element or kth element, I have to just add k to it simply. This is just because each element in this array is as big as 1 byte. But in the next array, each element is 4 bytes. So accessing the kth element is a bit different. So as base address, we have POW2, which is this address, and we have to sum it up by not k, rather 4 times k, because each element here is 4 bytes, not just 1 byte. So in your assignment, you are going to work with arrays, but it is actually simpler than what I have taught you here. But I just wanted you to have the intuition about how memory management works for storing arrays on MIPS memory. So now let's see another example. We want to work with a simple array, and for that, we just want to print out the elements in an array. So we want to print out the elements in an array. So first I need to define my array, of course. So I start by data directive. I give it the name list, for example. And I want it to contain 32-bit numbers. I put some numbers here, and I want to later on print it out, but I want its numbers to be separated by a space. So I need to even define that here. So there is some spelling here. Yes. So I define space character here. Otherwise, these values would be printed one after another. So I don't know which is which. Because, for example, I could have 2-digit numbers or 3-digit numbers. I don't want them to be mixed up together. So then let's add the size of this array so that I know how many elements I am going to print. This makes my work easier. So I want it to be, so how many numbers do we have? 3, so I have 6 elements. Because I cannot go beyond the size of the array. We don't know what is stored there on memory. Okay, the data part has finished. Now I will start my program. So let's first get the address of the beginning of the array. As I said, that address is given to us by this variable. So I need to load that address using LA instruction in some register. So I load that in register, load the address of the beginning of the array. Okay. After that, because I want to implement a for loop to print out this array, I need to have some sort of loop counter. So I start by 0, so I load an immediate value 0 to another register, for example, T2. Or I could use 0 register itself. But anyhow, so I want to start from 0, but I don't want to continue more than the size of the array. So I need to load the size of the array in some register as well. So here, this is a word as I have defined it here. So I use LW instruction. I use another register. Make sure that you don't use the same register. For example, I could use register T1 here, but then I would not access to the address of the array anymore. You should be very careful about which registers you use. So here I load the size in T3. Okay, now I want to have a looping mechanism because I want to go back to the beginning of the loop. I need to have some label that shows me where is the beginning of the loop. Loop start or loop beginning. So you see labels are used for many purposes, for defining variables, defining functions, defining for loops or while loops, whatever. So here I want to see whether or not I have reached the end of the array. Because if I have reached the end of the array, I should not print anything more. So I need to have another label that after the array printing finishes, I go there. So I will have a loop end label here. Okay. So if I see that I have reached the end of the array, I go to loop end. So how can I see that I have reached the end of the array? If I have two values being equal to T2 and T3 are equal, then I have reached the end of the array. So if T2 and T3 are equal, I will jump. This is conditional jump. I want to jump to loop end. Otherwise, the next line will be executed. So in this case, I want to print an element. So I have to first load it to some register, and then I will issue print syscall. So I load it. I always need to load it into A0 register, and I will load it in. So the address, you remember we had stored in T1. So I load T1 into A0 register. And then because I want to print integer, I have to load in register V0 the value 1. Then I issue syscall. So it is good that we assemble our code early. You don't need to wait until the end to assemble. Just let's make sure that we don't have any errors. So this is our array example. So it seems that there is a problem here. Yes, I have to say, specify the offset should be 0. So I am misspelling here. I forgot the $sign. Okay, now let's run it. Okay, we didn't have any assembling issues. Let's go back. So far we have printed one element in the array. Now we need to move on to the next element. So for this purpose, we need to increment our loop counter and also the address of the next element that we want to get access to. So T1 is, in this case, in this line, is the address of the first element in the array. But when we want to move to the next one, we need to
incremented by 4 because our elements in the array are of size 4. So each time we need to increment that with 4. So first let's increment the loop counter, which was T2. So this is our loop counter. So I increment T2 and I store the result in T2 as well. I increment it by 1. So I increment the loop counter. And I also need to increment the address of the element in the array. So that address of the element was in T1. I want to store it in T1 as well. And I have to increment it by 4 because each element is 4 bytes. And so I want to jump to the beginning of the loop to print the next element. So I do here in this case a J instruction. I don't need to use JAL because I don't have a function call here. I have a simple unconditional jump. So I jump there, and now it's time to implement the end of the loop instruction or label. Okay. So loop end, what do I do after finishing the printing? I can simply exit. For that, I need to load the value 10 to register V0, and I issue the syscall. So let's see. I run it. You see that I have printed all the array, but I have forgotten to print the space. So all elements are printed one after the other. That is correct, but I can just go back and add the parts that prints the space character. So for that, I want to first load the syscall code in V0. In this case, it is 4 because I want to print a string. Then I need to load the string by its address to A0. So the address is simply the name of the string, and I issue then the syscall. Now let's run it. So you see now these values are separated by space and are all printed out. So we have seen so far that assembly code could easily be converted into machine code, and it is an essential step in executing assembly code. Otherwise, the computer doesn't understand assembly. It's too high level for a computer. But it is interesting that binary code cannot be converted back easily to high level code. It is actually called reverse engineering if someone does it, and it is a very complicated task. You can Google a little bit about it and read about it and see why it is not a trivial task, and in many cases not possible to do this conversion from binary code to high level code. So if you have any questions, please make sure to reach us and ask your questions. And you have an assembly assignment for this module. You are given a skeleton, which means that it's an assembly file that has all the variables declared, it has all the functions declared, the function called, function returns, everything is done. You're just going to implement the code of 3 functions, and you are provided with a lot of help for every single line of code that you're going to write. So the size of the file, the skeleton file, might look big, but it is essentially not, because most of the things that are there for your help and for guiding you towards what instructions you should use. And at the end of the lecture, I have also put more instructions because during the lecture, I just introduced those that are most popular and you will use in your assignment. But there are more instructions that you can either see here or see in MARS. So if you come here in MARS help, click on help. And so let me use my magnifier. So here in the help, you can see the basic instructions, the pseudo instructions that we talked about. Basic instructions are those that are basic. They don't need to be converted to any simpler assembly. They are the real assembly instructions. And then you have all these directives that we talked about and even more. And then there are also syscalls that you can read about, and exceptions and macros are beyond the scope of this lecture and this course. So good luck and thank you for your attention.